Okay, good morning everyone. So the remainder of this class, so today's lecture what we're going to do is talk a little bit about mechanical and civil engineering and what those disciplines entail. That's largely the remainder of this subject. On Monday, I am going to cancel that lecture, so no lecture on Monday, and you guys can use that time to finish off your pump designs that are due Tuesday. So I'll say that again, no lecture on Monday. Please use that 2 hours wisely towards your final pump designs. Did anyone go to the workshop last night? So Nick and Pat were there Monday and Tuesday for you guys to go and use if you needed for your pumps. Monday night workshop next week is 100% devoted to that, but obviously it's the day before it's due. So if you've got major concerns or major problems, you're going to have a very busy night that night if that's when you choose to go and see Pat or Nick about it. But that's there to largely work out what drawings, do I need, what file type do I need, how do I make an STL, that kind of stuff. If you don't know any of that, then that's a good time to go and work that out. Today's lecture, as I said, will be civil and mechanical engineering. Next Wednesday's lecture, we'll talk about chemical and electrical engineering. And I want to give you a bit of a broad understanding of what those disciplines do, what sort of jobs those disciplines might complete, and also what you need to know about those disciplines if you're going to choose them, what JCU's version of those disciplines actually covers as well. So there's different flavours to a civil engineering degree depending on where you go, and I'll talk about what JCU actually does. Also, some of you will have seen on Learn JCU, I put a folder of past guest lectures. So in previous years, I've tried to get a couple of guest lecturers in from industry to talk about civil engineering, mechanical, chemical, electrical and so forth. This year, with all of our Monday public holidays taking away all of our lecture time, I didn't have an opportunity to get those guest lectures, but I've got the video recordings of about 6 or 7 guest lectures up on Learn JCU for you guys. I suggest all of you, when you have a minute, go and watch some of those. Perhaps in your specific disciplines that you're choosing between, but it's very worthwhile for everyone to know what all the other disciplines do as well. Discipline awareness is one of our subject learning outcomes, and it's really important for all engineers to know what all other engineers do, because you as an engineer need to be able to work in groups, and you won't be working in just mechanicals or just civils. You'll be working in, most of the time, cross-disciplinary teams where the electricals do the electrical work, mechanicals do the mechanical work, chemicals often maintain the whole process and oversee everyone, and the civils do the infrastructure. All right, so if you don't know what the other engineers do, then you might be trying to work something out that you don't need to. A civil engineer is very, very fast at designing structures and making sure they're up to code. A mechanical engineer doesn't do any of that sort of stuff in their degree in terms of what codes and standards are involved, and so you'll spend 3 weeks trying to find all of the right information that you need where it might have been an hour for a civil engineer. So you need to know those sorts of things because it's going to save you time. And also it means that when you're communicating with someone, you can talk on the right sort of level of, can you do this, can you do that sort of stuff, okay? So all engineers need to understand what the other engineers are doing, and that's part of why we have a common first year, and I'm introducing a little bit about that today. You also have the opportunity at the end of the year to go on the industry tours that Shelley organised. Has she sent out an email about that yet, or have you guys heard about those? So effectively, we organise buses, and I think there's about 3 or 4 full days where bus fills up with you guys. You go out to industry, and you might go to Extrata Copper, and then go to the Townsville City Council, and then the port or something like that. And you guys are taken on site and shown around different disciplines of engineering and what the engineers do. And there's lots of different opportunities to do that. That's at the end of the year. I highly recommend everyone go on those tours if you can, because they're really eye-opening. Even if you know full well what sort of discipline you want to be doing, then it actually helps you to think about what subcategory of that discipline, because as I'll talk about, each discipline has streams. So You know, just because you want to be a civil engineer, are you going to be a geotechnical engineer, or are you going to be a structural engineer, or what are you going to do? And those tours are really good. So keep an ear out on that. And then you've got all of your subjects in first year that hopefully expose you to the different disciplines. And if by the end of all of that you still don't know what discipline you want to do, feel free to come and talk to us. I mean, you can talk to us at any time, but if you want to know about mechanical engineering, come talk to me. If you want to know about civil engineering, go and talk to Rabin or John Ginger or someone like that. Madoc's an excellent person to talk to about chemical, and probably Ahmed or Owen or someone like that about electrical. Okay, so there's all of us at your disposal to have a quick chat about what discipline you want to choose as well. All right. So I'll talk a little bit about civil engineering. You've got a sheet in front of you. We're going to do a bit of an activity, take a couple of minutes. Hopefully everyone remembers their grand challenges. You see that your grand challenges are down the left there. We'll talk about civil engineering, and then I'll talk about mechanical engineering, and we'll do the same thing. This diagram here, has anyone seen this diagram? Probably not. This is a streams diagram. So I've made these diagrams for every one of our disciplines. We're using it for accreditation and also to help you guys understand the context of your subjects. Just for the minute, I might turn the light down so you can see it a bit better. Unfortunately, with the lights down like this, the video turns out really, really grainy and horrible. So I prefer not to do it, but obviously for stuff like this, you need to see the screen. So if you can interpret this, this is your first year. We are in S1 here, so that's us sitting EG1000, S2, and then year 2, year 3, year 4, and so forth. Okay? And so the subjects that you do in each discipline can be categorized into a stream. All right? And so you've got 4 electives, obviously. They're the grey ones. The first stream we have here is engineering management, and EG1000 for the civils is largely what your exposure to engineering management is. That's pretty much our last lecture, except for a full subject with a project focus. So you do a project for that entire semester, you deliver it, it's an industry-based project, and that's your exposure to what project management is. I think the chemicals and the mechs do a little bit more in project management, but otherwise that subject is a really good basis in project management. And then there's 3 other streams in civil. You've got geotech, you've got structures, and you've got water and hydraulics, and I'll talk about each of those. And then you have a couple of other little subjects around. These subjects are sort of capstones, so they kind of use information from all of those streams, so like a design project or whatever, and obviously thesis. And thesis kind of requires that you've done all of your degree and you might have a topic on one thing or other or something that sort of bridges all of it. Okay, so for civil engineering, you've got 4 main focuses. Project management, geotech, and so geotech is soils, it's any sort of foundation design and piles. So that 820, 830 metre tall building in Dubai, what is it, the Burj Khalifa? That building is built on sand. How much engineering do you reckon went into the foundations of that building? A hell of a lot. How much does an 800 and something metre tall building that's made out of concrete and steel weigh? A lot. So in those sort of circumstances, the engineers, they had a whole team of engineers before you even poured a footing, working out how long does the sand last, and then how long does the sandstone last, and then at what point do you get to the bedrock, and if the bedrock's a kilometre down, are you able to drive a pile that deep and actually hit it? Probably not. And so if you see the design for that building, it's actually got a giant big sort of a star that's probably 20 times the footprint of the actual building that you see, that spreads out across the land and then has thousands of piles, which is basically a big bit of concrete and steel that sticks down into the ground, that sticks down and holds it and tries to have as strong a foundation as possible. And I seem to remember hearing that even with all of that, they assumed, or they calculated, that the building was going to consolidate by 1 metre or 2 metres once they actually added all the floors on. And that was in the design as well. So in terms of a lot of geotech is what are your foundations, what are your materials, do we need piles, do we need concrete, do we need to get down to the bedrock, or is the rock that's at the surface okay, and how do we actually carry the weight of the structure. Rocks, particularly in mining applications and stopes. Does anyone know what a stope is? No? Good. So in mining, there's lots of different ways to cut the stuff out of the ground, but stopes is one way, which is basically you cut a big channel out and you have a tunnel down at the bottom and you take all the rock away as it collapses down, and you've got to hope that the walls of that don't collapse, because that might be rock that you don't want, and certainly if it collapses and you've got an excavator under there, that's a big problem. So you've got to actually make sure and design your stope around the structure of the rock and the fact that it's not going to collapse and that kind of stuff. And then you've got to fill it up with something because you're about to dig next to it. So you fill it up with some sort of a concrete-y, slurry structure that then solidifies, and then you cut out the next bit out of the mine. And there's all sorts of examples in mining and that kind of thing where a civil engineer has to actually design the process because they're the ones that understand the way the rocks and faults and things work, with help from geologists and so forth, obviously. Tunnels. Everyone's seen those big, crazy tunnel drilling robot things, big worm that drills through. Civil engineers need to design, the actual structure and work out how that integrates with the environment. Mountain roads, cutaways, open cut mines, and any sort of stabilisation of geological features. So if you've got a mountain, you've got a bunch of houses on it and there's mudslides and things, a civil engineer or a geotech engineer is the one that comes in and works out how to stabilise that slope such that it all doesn't just end up at the bottom of the mountain, buildings and all. And here's just some pictures on that. So the top one is one of those tunnel cutting machines. They're getting more and more popular. You've got those going all over the place. Has anyone heard about the one that they cut through Boston, basically under Boston City? So you've seen the Brisbane one, obviously. The Brisbane one they did a really good job of. The Boston one was far more complicated than the Brisbane one because you had 300-400-year-old structures and buildings and high-rises and all sorts of things, and you're cutting these tunnels directly under those. And so they were finding that they'd had to stop a lot of the time and reevaluate because the surface buildings were moving too much in the drilling and that kind of thing. So they ended up something like $40 billion over budget and took about 3 times as long as they intended to take, because some of the engineering perhaps, you can't do engineering in some circumstances that deep until you actually get there. And some of the actual issues that they came across were really challenging, and so civil engineers had to do a lot of work on the fly for that. And then unfortunately it finished and some of the ceiling tiles started falling out of the roof because they made it pretty cheaply, and they had a lot of issues about that too. But in the end it ended up being an amazing tunnel system through one of the oldest major cities in the world. It was very good. Open cut mining, there's an example there, and here's a big landslide. And so that landslide, civil engineers would have to work out how to stabilise that, particularly if there's roads anywhere near it, or tourists or houses or anything like that. Civil engineering, geotech needs to work out how to stop that. All right, so that's geotechnical. Anything with soils, rocks, the ground, that kind of stuff, and design and maintenance around that. Another area that civil engineers deal with is water and hydraulics. And so not necessarily water going through pumps, but more things like water in terms of catchments, runoffs, lakes, wastewater, that sort of stuff. And also water in terms of things like the ocean. And you have a lot of structures like piers and oil rigs and our pretty strand structure and things like that civil engineers need to design such that it doesn't get washed away when the water happens. So this is an example of water. You've got what on the top left there, we've got a little lake, and that little lake is one of the ones that is going in around the new housing developments around Townsville. And those lakes are very carefully designed because they have a lot of reeds and things like that that actually catch a lot of the dirt and crap that the runoff water collects on its way through, such that that gets caught by those sort of marsh catchments and then the water gets taken away into the stormwater drain. If you just took it straight down into a stormwater drain, you'd have a lot of garbage and you'd have to be cleaning it periodically, and it'd be clogging things up. And as soon as it'd clog, it'd overflow and then all the houses would get flooded. So it's very important that you've got good designs to actually get that runoff water, clean it and get it away from the housing developments, and that's all civil engineering. Dams, where do you put it? How do you build it? What the hell happens to the water once it's there? That's all civil engineering. This is part of, I think, a catchment water, so that's again runoff, where does the stormwater go? And this is a sewer, and all of the sewer designs, the way the water goes and all of that kind of stuff, civil engineering around that water. Coastal engineering is the other aspect of water that civils deal with, and coastal engineering can be anything from what we've got here on the top left, which is a marina. On the top right, everyone's seen the reclaim stuff they're doing in Dubai, yeah? United Arab Emirates and various other places. So effectively you're out in the ocean, you're just filling it with a bunch of rocks and sand and turning it into an island and then building high-rises on it. Obviously you've got to make sure that tides and things aren't going to wash all of your brand new multi-billion-dollar islands away, particularly once you've got a high-rise and a bunch of tourists on it. So all of that, the way that the current works and the way that the water has to flow around the new structure is civil engineering. When they actually put this one in, it was actually pretty interesting. I don't know if you've seen the documentary on it, but obviously oceans have different currents and tides and things like that. And what they actually found was once they put this in, it changed the way the tidal currents worked. And so they, instead of depositing sand, and sand on a beach isn't something that just lives there, sand is deposited and taken away constantly with the tide. And so within the space of a couple of months of having some of this structure in there, half of their beach was bare and the other half was a massive big pile of sand, because the way the currents changed, because this was put slap dang in the middle of where all of that water flow was happening. So now what they have to do is have hundreds and hundreds of trucks shipping sand from the desert to their beach that keeps getting emptied of all of its sand because this structure's there. So they didn't anticipate that. Perhaps they could have done more civil engineering on it. But now they've got this problem that for the rest of forever, they've got to truck sand to their beach because it keeps getting washed away because they've got this big structure in the way. This is a similar sort of thing. So this is the sort of structure that stops your sand washing away, particularly if you've got buildings built on your sand. Anyone that has seen any news reports around the Gold Coast and all of their multi-million-dollar mansions that are built right down on the sand, and then the sand washes away in a big storm and the mansion falls down, or is threatened with that. A lot of civil engineering going into making sure that doesn't happen. Has anyone seen these things? These they scatter them all over Japan, particularly on waterways, and these are put in place to absorb energy from tsunamis. So a tsunami comes in and hits these and loses a bit of its kinetic energy, and so it goes less far into the mainland. So these are there to absorb some of the damaging energy of tsunamis, and they've got these all over waterways and all sorts of things over there in Japan. And this was the design and the shape that they worked out. Took the most energy and moved the least when it got hit with water. So interesting problem they have to deal with, but that's civil engineering for you. And then the last one. And this is structural. So this is kind of the backbone of civil engineering. This is the stuff you guys did in the beginning of the semester. You built a bridge. So structural is pretty much design of anything else, be it concrete, steel, timber, anything that needs to stay up. And so there's our example of that Burj Khalifa or whatever it is, Sydney Harbour Bridge. This is a crazy building called the Starter Building at MIT, which is all sorts of Dr. Zeus looking. And someone had to actually design all of that structure.
There's a crazy building in Shanghai that it actually looks like a pair of trousers. So it comes straight up like that, and then it comes back horizontally and meets up in the middle.
Oh, really?
Yeah.
Yeah, crazy. So a big cantilever thing. Yeah, well that would have taken some civil engineering, that's for sure. Yeah, so all of that sort of structure. Our building 15 has a nice big cantilever. Obviously that's civil engineering. How does that stay up? How does Paul Dirks' office not fall down into our little pond there. So anything that, basically a building structure that needs to stand up, that's structural engineering. And so you'll learn how to design the structure to carry that load. All right, so I'll get back to this image. Those are the major streams of civil engineering that you'll cover at JCU. You've got subjects there as well, and some of the subject description, it's a bit small to see there, but once you actually have these notes on your computer, you can read those subject descriptions and it'll give you a little bit. If you look up JCU 2016 and the subject code, so EG1000, in Google, our CSDB, so the subject database will come up and you'll be able to read the full description and all the learning outcomes and everything like that to every subject at JCU. So if you want to learn a little bit more about any of these subjects, then just look up JCU 2016 and the subject code, and even the subject name will help you out in Google, and you'll come up with the first entry should be that subject and all the information on it. Okay, so when you're making your decision of discipline, if you're undecided, then that's the sort of thing that I suggest you do. You start to look at what these subjects entail and what you will be studying, how it evolves within these streams. Okay, so now we're going to do a little exercise. You have your piece of paper in front of you, and under the civil engineering left-hand side of it, you have engineering management, geotechnical engineering, structural engineering and design, and water and hydraulics. And very simply, based on the description I've given you, and feel free to Google and talk amongst yourselves, you're going to go through and put a tick in any box that applies to those grand challenges. So fundamentally, engineering management, probably not going to get any ticks in it because it's not necessarily a grand challenge so much as a skill that everyone has to have to implement everything. But a good example, perhaps, where's my ticks? I think, what do we got? So restore and improve urban infrastructure. Which one of those civil engineering streams would be dealing with that? Definitely structural, so structural engineering is building design. What else? Sorry? The water one? Yeah, so water and hydraulics, you need to get all of the sewerage out, you need to get all of the water in. If you're building new cities, you've got catchments and so forth. So go through these and think about what I've just talked about a little bit and see which one of those grand challenges apply and put a little tick. And then if this was a question on a quiz, I would also ask you to explain a project of one of those. So for example, if I'm going to choose structural and restore urban infrastructure, and I asked you for a project, it wouldn't just be telling me those words, it would be a civil engineer would design a new high-rise building to accommodate a certain amount of people and be able to design that building to deal with inclement weather and climate change or something like that. That's a specific project that an engineer would do in that area. So just do ticks for the moment, but think about what sort of project each one of those ticks might represent. Take about 5-10 minutes for that. All right, let's just do a couple of these ticks here, guys, and then we'll move on to mechanical. Everyone see that? Yeah, cool. All right, so are civil engineers doing anything with making solar energy economical? Probably not. Probably not. Not unless you're putting solar panels on a roof or turning a solar panel into an actual roof tile or something like that. Maybe that's civil engineering, or certainly civil engineering would be involved in that, but otherwise not so much. Provide energy from fusion? Anyone? Structural engineering, and in what way? Yeah, the actual plant building, whatever. If you're going to have a fusion reactor, you need an actual building around that, and certainly civil engineers will be very closely involved in that. All right, develop carbon sequestration methods. What's carbon sequestration? Pump carbon dioxide in the ground mostly. And so where would a civil engineer be involved in that? Structural probably, and geotech definitely. So geotech is rocks, soil, sand, how does that work? And potentially structural as well, but mainly geotech. Maybe even water and hydraulics because you've got groundwater there, and a big issue is carbon dioxide leaking into groundwater around a reservoir. So potentially all of those. Manage the nitrogen cycle. So nitrogen we use as a fertiliser. Runoff of fertilisers is a big issue, and that fertiliser getting out into the reef and things. So I would say potentially water and hydraulics. Provide access to clean water. Water and hydraulics, definitely. Restore and improve urban infrastructure. We said that, didn't we? We said probably this guy, and maybe even geotech, depending on your foundations and things. If you're building very, very tall buildings, you definitely need geotech engineers doing that. Health informatics, probably not a civil engineering game. Medicines, certainly not civil engineering. Brain, not so civil engineering. Nuclear terror, maybe if you're building nuclear bomb-proof buildings, but that's a bit up there. I'd rather it not drop than we're impervious to it. Cyberspace, virtual reality, personal learning. Tools for scientific discovery, you might say structural because you need to discover science in buildings, but otherwise. Cool? Alright, so that was a little exercise just to make you guys think about what I was just talking about more so than just have a lecture. We're going to do that for mechanical in a second. Let's get to the mechanical slides. Alright, so before I go on, any questions, additional questions on civil engineering? That's a very, very brief overview, so there is a lot more information to learn about what civil engineers do, but hopefully that opens your eyes just a little bit to some of the possibilities in civil engineering. Okay, so this is mechanical engineering. Exactly the same as before. We've categorised them into streams. You've got your minor subjects there, and you've got your thesis that kind of sits over the top of it in fourth year. Otherwise, we have engineering management. Have I got one on that? No. So engineering management, we do the same EG1000 subject. Everyone does that subject. Mechanicals and I think chemicals do asset management and reliability on top of that. So that's the sort of next level of project management of how do you maintain your assets in a mine, refinery, plant, workshop, whatever. How do you make sure that they're going to work? How do you replace them when you need to and that kind of stuff? So that's the next level of project management. Civil engineers don't have a lot to do with that. They're much more project management of large, infrastructure projects. Mechs are much more likely to have at least some aspect of maintenance in an industry role, same as chemicals and possibly electricals, but mainly chems and mechs. Then we got mechanical design. That's the stuff I deal with. We got materials, dynamics, control, and thermo fluids. So I'll talk very briefly on each of these, less briefly on the mechanical design one because it's the one I like, but we'll get through. So mechanical design is basically building machines, anything that moves. All right, so if you look at your car, anything that doesn't have electricity flowing through it, a mechanical engineer designed. And they had to design that to make sure that it's going to last for 300, 4,000 or 400,000 Ks or whatever that car is going to last for. Within, maintenance and things, there's certain things you maintain, but chances are in that 400,000 Ks, you're not going to replace a piston and you shouldn't have to replace the cylinders and things like that. So the major components of the car should stay there, and then you just you maintain it with replacing oil and that kind of stuff and various timing belts and that kind of thing. But all of that needs to be designed by an engineer, a mechanical engineer, and you need to understand the materials, you need to understand the forces, you need to understand what happens to things when they have repeated forces on them as opposed to static forces and all of that sort of stuff. And we use a lot of SolidWorks, we use a lot of FEA programs and things, which is simulation. We do a lot of hand calculations and AS standards, and all of those things kind of have to agree with each other. And once all of those things agree with each other, we're confident in a design to go and then do maybe some experiments on. And if you're going to mass produce something like a car, you've seen some of the high profile recalls lately. The amount of money that a Toyota recall costs when Toyota put out the numbers of vehicles that they do is billions of dollars. So if you stuff something up by the time it's at market and you sold a bunch of them, it's going to cost you just insane amounts of money to fix that problem. So the idea is that the design process makes sure that doesn't happen. Design process for a car is roughly 10 years from concept to actual market. Much less for lower production stuff, but anything from all of the machines and conveyors and hoppers and everything in a mine to this. It moves. A mechanical engineer did that. Yeah? And the fact that I just smashed it down there relatively hard, and if someone got really grumpy at an exam and, let it go, you have to design it for that it doesn't break, because if it breaks then it's a sharp edge and it might hurt someone and that kind of stuff. So literally every little device that moves and does anything, mechanical engineering. Alright, so some of you might have seen this. This is our FSAE car. This represents exactly what I'm talking about in terms of design. You lose some of it without the noise, I guess. So this is competition in December last year. This is our first car that we've raced on a track. Alright, so you get the idea. Basically, every part of this car is mechanical engineering design. So every bit that moves, the suspension that goes up and down, the uprights that are made out of aluminium, the bearings, all the air intake and exhaust components of the engine and the engine itself, the chassis. So, that's mechanical design, and we use a lot of tools to actually design everything. So it's not just that, it's just that's a really nice little project that we can actually do. But the same theory that you put into that car is the theory that you put into a conveyor belt for, some Mountizer mine somewhere, or, any of this type of stuff that I was talking about. That's all mechanical design. We use a lot of numerical modelling, so we can do numerical modelling of solids like this, and that tells us what the stress is, so force density within a material. Materials break when stress is high, so if you know where the high stress is, you know where it's going to break. And we can also do things like particles for excavators and diggers and conveyor belts and hoppers and all of that sort of stuff. And this is just an example of that. So this is a whole bunch of little DEM particles, so little spheres, going through a hopper, and what you want to do is make sure that that material doesn't get caught up somewhere, particularly if it's things like food and grain. What you don't want is that grain to be stagnant somewhere, because then that goes off and the other grain comes past it, maybe picks some up, and then you spoil your entire production. So you need to make absolutely sure where it's all going. In binding, you need to make sure that you're not wearing out your components too quickly, and you need to understand what wear properties and things happen from moving particles like this. So you do all of that design using the numerical methods. It's all mechanical design. Okay. Alright, so I'll go through these three quickly because I don't have specific examples on them, but materials is anything related to strengthened materials, modern and advanced materials, and testing of those materials. So if you're producing a vehicle for large-scale production, you need to understand your materials very well, and you're building, carbon fibre, this, that and the other. You need to understand how to test that carbon fibre and make sure that it's not going to break at, 100,000 Ks or whatever. So all of that testing is in this stream. And manufacturing techniques, so CNC, mills, lathes, 3D printing, laser cut, all of that sort of stuff. So how do you manufacture different things for production? The dynamics stream, spring mass damper system, so you guys will be doing a little bit of that in statics and dynamics next semester. So spring mass damper system, the suspension in your car is a spring and a damper. All right, so you've got the shock absorber, which is the damper, and the spring. The spring cushions and the shock absorber slows the actual movement. So if you just had a spring on your car, you just bounce pretty much forever down the road like this. The damper is what you put there that then slows that to almost negligible. So you just have one bump and that's it, rather than you see some cars that are old and have terrible dampers and they're bouncing down the road like this and off they go. So that type of system and the theory behind it, the understanding of that is dynamics. As is vibration analysis. So if you have a piece of processed machinery vibrating, you can actually put an accelerometer on it and tell the manager, all right, this bearing's going, or that shaft's going, or the impeller's going, or which bit is failing. You can tell which bit's failing based on a frequency. All right, and so there's that in it, and motion analysis of, how does a suspension or how does any sort of crane boom or something move relative to itself. Control is any sort of electronic system that controls a mechanical system, so you can't be oblivious to that. You need to understand that. Things like ECUs and conveyor systems being run by motors, and those motors being controlled by computers and that kind of stuff. And then thermo fluids. We do quite a lot of thermo fluids. Thermo fluids is another really important area of mechanical engineering, and that's anything related to air conditioners, refrigerators, pumps, pipes, solar radiation, solar energy, so, solar cells. Heating, so heaters in your car, heaters in your house, heaters in an actual, how do you heat up or to dry it in a process, and heat removal being radiators and any number of other methods around that. All of the theory and design around all of those different aspects of anything heat or cold, anything water or fluid or air, and that's thermo fluids. And so large-scale air conditioning systems, refrigeration systems, pipelines, pumps, etc. All of the design of that is mechanical engineering. And we also do quite a lot of numerical modelling thermo fluids, so that's modelling fluids like water in pipes, like air around sails and aircraft and cars and all of that kind of thing. So a lot of numerical methods involved in thermo fluids as well. And the last two slides I have is just a couple of examples from my research, and then we'll do the last example and we'll be done. Some of the research that I do, I think I might have mentioned about the artery research, maybe in the first lecture. But what we're trying to understand is the way that blood flows through abdominal aortic aneurysms. So that's a sort of an expanding of the artery and a weakening of the wall. Bit of an example there at the top. If you've got an aneurysm, you probably got no symptoms. If you've got an aneurysm that bursts, you've probably got dead symptoms. And that's pretty much it. So we need to understand whether we need to operate, whether it's likely that the person will have a rupture, or whether we don't need to operate. And so we do that with FEA modelling, which is kind of that design stream, and we do that with fluid modelling, which is the thermo fluid stream. And this is another example of thermo fluid. So this is a couple of years back, we analysed the air intake of the CBR 600 engine in our car, in the FSAE car. On the left there, you've got an experimental apparatus with inserts, and we had a bunch of different inserts on the plenum, which is the main bit where air goes in. Does everyone understand, or anyone understand internal combustion? So you need air, you need spark, and you need fuel. All right? Anyone that, when you put your foot down on the accelerator, literally the only thing that's doing is just opening up a valve and letting more air into the engine, and then the ECU works out how much more fuel needs to go in with that. But effectively, your foot on the accelerator just says more air, you take it off, it says less air. That's it. All right? And so this is the part where that air actually comes in and collects before it gets sucked into the engine. And so the volume of that is really important for power. If you have the right volume, then you'll have the right power. And so we did a bunch of experiments with different inserts on volume, and we did a bunch of numerical tests to work out those different volumes, and these are flow paths. So obviously this messy flow path, for the same reason that you don't want sharp edges in your centrifugal pump, you don't want messy flow in your intake, because you're losing energy and that air is then not going into the engine. You have worse performance. Okay? So we did all of that, and all of that's thermo fluids, that numerical methods to try and optimise power and performance. Cool. All right, so now let's go through for the next 5 minutes the last little exercise. Think about those streams that I've talked about in mechanical, and think about how they frame next to the grand challenges for engineering, and then we'll be done for the morning. Okay, has everyone had a bit of a go at that? You started to think about those streams as they relate to these? All right, let's just go through them quickly. Make solar energy economical. Which streams might be involved in that? Design, potentially, yeah. So you might be able to design different systems. Oftentimes, economic solar tracks the sun and things like that, and so those moving mechanisms, definitely mechanical engineering. What else? Yeah, so thermodynamics, thermo fluids. So you do quite a bit of information on like solar energy and efficiencies and how that actually works, and also solar hot water and that kind of stuff in that stream. Anything else? Maybe control, but that might be a bit more electrical. Yeah, so materials and manufacturing. So if you're going to make something more efficient, then making it cheaper to build is probably a good way of doing it. All right, what about provide energy from fusion? Yep, thermodynamics, a lot of heat going on. What else? You probably got mechanical design in so much as there's lots of moving parts in there. Anything else? Probably a few more there, but that's okay. Develop carbon sequestration methods. Yep, definitely thermodynamics. So what you have to do is take gaseous carbon and turn it into liquid carbon, and that process is a bunch of machines and compressors and all sorts of things. So definitely that, definitely mechanical design as a result of that as well. Anything else? Probably not. Manage the nitrogen cycle. We've got mechanical engineers doing anything with nitrogen, probably less so than chemical engineers and probably less so than civil engineers. But, maybe there's mechanical design there, but it'll be, adjacent systems or whatever. Access to clean water. Yep, mechanical design and probably thermo fluids as well, on account of there's pumps and all sorts of things. Oh, hang on, that's nitrogen cycle. There we go. Anything else? Dynamics? Yeah, possibly. So dynamics and thermodynamics. Yeah, dynamics might be in the actual way that you mount pumps and things to minimise and mitigate vibration and analysis thereof. Restore and improve urban infrastructure. Yeah, materials. So how do we actually, what do we build them out of? How do we build them? What else? How do you get to the top of an 820 metre tall building? A crane? Well, you need a crane, yeah, but if you live on the top floor, how do you get to the top? Stairs? An elevator. Elevator, there you go. Guess who designs elevators? These guys. How do you get water to the top of an 820 metre tall building? Pumps and pipes. These guys. All right, advanced health informatics, that's sort of basically, what do we say, Fitbits, so maybe not so much. Aside from the fact that a Fitbit has to not break when you hit something and it's got a little clasp and things. Engineering better medicines, probably not. Reverse engineering the brain, maybe in a bit of modelling, but that's more research end of the spectrum, so don't worry about that too much. Prevent nuclear terror. I don't know who's preventing nuclear terror. Maybe governments are preventing nuclear terror, so I don't know how much of a problem that is for us, but it's, whatever. It's a big problem for everyone if we can't do it, that's for sure. Secure cyberspace is much more electrical than mechanical. Enhanced virtual reality is electrical, other than if you've got a virtual reality mask and things, some of the clasps and things, that's mechanical. Advanced personal learning is definitely computer systems and so forth. Engineering tools for scientific discovery could be any or all of these, so let's just do these. Basically, that's building scientific apparatus, and so that's mechanical design. There could be pumps in thermo fluids. It could be heating things up. It could be controlling things or moving things. So any of those. So now, if I was to ask you a quiz question, and guess what? There's a quiz too, so I'll be asking you quiz questions. It might be for you to explain a specific project on one of these areas, okay? So that's a really good area. For each of these ticks, just write down a sense of what a project might be that an engineer would work on, and then you've studied this lecture, okay? Cool. Thanks, guys, and I will see you not Monday, remember? So no lecture on Monday. Everyone's handing their stuff in on Tuesday, so I'll see you then or before if you have questions.